Welcome everyone to today's webinar. I'm just looking at the people logging in here today for the broadcast. It looks like people are still coming in pretty heavily. So we'll just give another minute or two to allow people to get settled and figure out their audio before we begin the official presentation. So thanks for being on time, and thank you for your patience. And those that just logged in, just want to let you know that we're going to get started just in a moment. There's quite a few attendees still logging in, so we'll just give them a chance to get settled and get their audio figured out before we begin. Welcome everyone to today's Veolia Water Tech Talk called Advanced Water Reuse, Fiber Recovery, and Wastewater Treatment Strategies for Recycled Pulp and Paper Manufacturers. My name is TJ Willits, and I'll be your moderator for today's technical presentation. Just some housekeeping items to get through before we get to the technical part of our presentation. You should be hearing me speak now. If you're having trouble with your audio at any time throughout the broadcast, there's two methods to listen into the audio portion. You can either listen through your mic or speakers on your computer. If you have issues with that, you can go ahead and switch to a phone call method and use a dial-in number and listen over the phone if you have trouble with your computer. Just to let everyone know that today's broadcast is being recorded, and it'll be sent out about 24 to 48 hours after the end of the broadcast to your email, so you can go ahead and watch that on demand. Now, everyone's microphones are muted. However, we want to make this as interactive as possible for you to ask questions about the subject content and interact with our panelists. So to go ahead and do that, there should be a panel with your GoToWebinar, maybe on the right side of your screen. You can go ahead and enter that into the chat, and we'll get that, and we'll ask as many questions as we can at the end of the presentation. But feel free to enter them in throughout today's broadcast, and like I said, we'll get to them hopefully at the end. Now, today is a webinar dedicated for recycled pulp and paper manufacturers, but we do have a couple other webinars. I know there's some engineering firms that are on the today's broadcast. So if you want to attend one of our future Tech Talks, we have one on sustainable wastewater treatment and biogas solutions for distilleries, and that's on March 8th. And then we also have one related for food and beverage companies. It's about solving your wastewater reuse challenges using membrane bioreactors, or MBRs. And that's a week later on March 15th. And you can register for those webinars at the website shown on your screen. Now, in addition to the live webinars that we have within our Tech Talk program, we also have 60 or so on-demand webinars available to watch anytime on demand. Again, that's on our website, veoliawatertech.com. Now, for those in attendance for the live broadcast, a day or two after the broadcast, the live broadcast, you're going to be receiving a PDF certificate. You can use that for logging continuing education credits, or just to have as a souvenir for today's broadcast. So be on the lookout for that in the follow-up email. Oh, this is important too. Right at the end of the webinar, all the participants will be taken to a survey. And for people that take that survey, we're going to enter you in for a $25 Amazon gift card, just as a thank you for just taking about 30 seconds of your time to fill out that survey. It really helps us improve the quality of these Tech Talks and also hear feedback of what you might want to hear as for future topics. So a little bit about Veolia Water Technologies. We provide water and wastewater treatment services, projects, and technologies to a variety of customers. And you can see those, we do that through engineering and procurement by putting processes together that are able to take influent and treat it to a required effluent specification. We also invent and develop and improve and install really innovative technologies within this space as well. And of course, we support our customers through a wide range of services that also are related to water and wastewater treatment. And of course, we work in a variety of industries, industrial as well as municipal. And you can see those on your screen. Now, when we look at pulp and paper, we're a very unique company. We are multifaceted in what we do. We have, of course, a wide range of water and wastewater treatment capabilities. You're going to hear a lot about that today on today's technical presentation. But in addition to that, we do a host of evaporation and crystallization technologies and services as well. So we work within the black liquor evaporation cycle. We also provide capabilities and services and technologies to help enhance the recovery boiler and treat precipitator ash, and also recover chemicals as well from that particular process as well. So that's sort of what we do for our variety of customers around the world within pulp and paper. In terms of our experience with pulp and paper, we do have quite a bit. We have over 35 years of experience within pulp and paper, and we have almost 1,000 global references with several trusted pulp and paper companies across the globe. And it's something that is a key industry within Veolia Water Technologies, and one that we have a lot of process experience, a lot of background information, and a lot of technologies geared for this particular industry. So now let's get into today's presentation. I'll go through the agenda a little bit, and then we'll meet our panelists in just a moment here. So what we're going to hope to cover today, we're going to take a look at the wastewater trends and outlook related to pulp, recycled pulp and paper, and fiber recovery and water reuse. We're going to take a look at that today. And after that, we're going to look at some of the strategies that are used to enhance sustainability and optimize those water circuits and recover fiber that can be reused within your production. And of course, that's mainly going to be within that whitewater and de-inking loop, and we'll look about the technologies and some strategies used for that particular area of a mill. And then we're going to sort of go down the pipe, if you will, and take a look at the wastewater facility. Take a look at the process that it seems to be working really well when we start to optimize these water circuits and see what kind of wastewater treatment, technologies are needed to treat that water as we start to reuse that water more and more, and start to concentrate some of those things within that water stream. And of course, like I said, we're going to have that Q&A session on the back end of today's broadcast. So let's take a look and meet our two panelists here. The first panelist that you'll hear from today is Chris Harvey. He's the National Sales Director and Biological Wastewater and Process Improvement Specialist here at Veolia Water Technologies. He has over 20 years of experience in biological wastewater treatment. He's experienced in all kinds of different processes, from anaerobic treatment to activated sludge to MBR to SBR, oxidation ditch, biosolids processing. He has experience within starting up, design, wastewater treatment process design, commissioning, troubleshooting biological process as well. In addition, he has biosolids experience with sludge dewatering, aerobic sludge digestion, anaerobic sludge digestion, food waste and co-digestion, and of course with that biogas experience, biogas cleaning, handling, and getting that treated for renewable natural gas resources. In addition to Chris, we have a second panelist that we're excited to talk with today, and that's Joseph Walco. He's a technical sales manager and a DAF and water and fiber recovery specialist with Veolia Water Technologies and Solutions. For the past 23 years, Joseph has been working with the Poseidon DAF clarifier technology and helping industrial clients with a real strong emphasis within pulp and paper. He has over 35 years of experience completely within recycled pulping and water treatment equipment for the industry as well. So we'll hear from him in just a moment. But at this time, I'm going to hand the webinar over to Chris Harvey. Chris, are you with us?
Thank you, TJ. Good afternoon, everyone, and welcome to our webinar. My name is Chris Harvey, and I'm excited to be co-presenting today with my colleague, Joseph Walco, on the topic of fiber, water, and wastewater in the recycled pulp and paper industry. The paper industry has undergone significant manufacturing changes in the past few decades, as it's embraced the use of recycled paper in their mills as a raw material. There are many sources of recycled paper available to the paper industry, including OCC, ONP, OMG, RMP, MOW, and other sources. According to the American Forest and Paper Association, 68% of all paper consumed in the United States was recycled in 2021, steadily growing from about 35% in 1990. As a benchmark, in 2018, 24% of municipal solid waste was recycled. That highlights the paper industry's commitment to sustainability. New processes inside the mill have had to be developed to enable the recycling of fibers in the paper industry. Paper fibers, on average, are recycled 5 to 6 times, with 20% of the fibers being lost in processing due to reduction in fiber length and strength during cleaning and refining processes. Pulp and paper mills have had to be converted and upgraded to be able to use and process a combination of all these different types of recycled paper in combination with virgin pulp. The final product of these mills, including recycled pulp, corrugated boxboard, fluting, linerboard, fluff, as well as tissue and toilet paper. The paper industry is a large consumer of water, consuming thousands of gallons of water per ton of paper produced. Water is used to solubilize and clean the recycled paper, enhance the characteristics of the recycled pulp through the addition of water-soluble chemistry, convey the pulp, as well as dilute it so that it forms a consistent mat on the forming section of the paper machine. Water is one of the most important raw materials used in the paper industry today. Another key ingredient is starch, used to increase paper fiber strength, as well as to stick the fluting between 2 layers of linerboard to make corrugated cardboard. Starch use is increasing in mills as more recycled pulp is used and as paper thickness and weight decreases. Sustainability is at the forefront of the paper industry, so conservation of water resources is a key license to operate. It is expected by their customers. Water can be recycled from various places inside the mill, as well as from the final effluent back into the mill. The degree of closure of the water circuits depends on the type of mill process and the various costs of production. Some form of water treatment is likely to be required to enable water reuse to avoid issues related to final product quality. Paper mills are also large users of energy, both steam to heat the process and dry the final paper product, and electricity to power the various pieces of process equipment and the massive paper machines. Converting paper into biogas is a way to either generate green electricity or to displace natural gas in steam boilers. Both can reduce a mill's carbon footprint. Biogas is a combination of methane and carbon dioxide generated by anaerobic treatment. In the future, there is interest to upgrade biogas to renewable natural gas to be used as a vehicle fuel. And finally, complying with environmental regulations is a necessity, whether it be meeting soil limits or complying with our NIPT's discharge permit. A mill should also be aware of new state and federal regulations that may adversely affect the mill, for example, PFAS. In the following slides, we will look in more details of the key aspects of fiber, water, and wastewater management inside pulp and paper mills. Now let's talk about sustainability and water optimization strategies inside a mill. As we mentioned previously, water is a key ingredient in the paper industry. The industry is one of the largest users of water and energy worldwide, with 5 gallons of water and 4 kilowatt hours of electricity needed to make a single cardboard box. Almost zero water actually leaves a mill with the end product, compared to a water bottling plant, for example. So there are opportunities inside a mill to recycle and recover water. As shown on this slide, there are various drivers for a paper company to explore water recycling, all of which make good business sense, either to maintain the quality of the end product or to reduce the impact that the mill operation has on the environment. However, recycling water can create operational challenges to a paper operation. Closing the water loop would concentrate up compounds that are added during production that would normally be purged from an open water loop where no water is recycled or reused. For example, high concentrations of organic pollutants in a warm, humid environment can encourage the growth of bacteria in the paper making process. This can produce slime or produce an unwanted odor in the final product. Calcium carbonate is often added as a filler. If the concentrations of this salt build up, it can trigger nuisance precipitation on the equipment and inside pipes, obstructing the flow of water and pulp. Non-fiber solids that are introduced into a mill with the recycled paper can build up and reduce the quality of the final product, whether these are stickies from adhesives, wax, or other inert materials that can form spots on the final product. Additionally, PFAS, or forever chemicals, is an emerging contaminant concern that we could dedicate a whole webinar to. We will briefly touch on this at the end of the webinar. There are both economic and societal drivers for mills to consider green energy generation from wastewater. Starchy wastewaters can be transformed into biogas using anaerobic treatment technologies. The biogas generated normally contains 65 to 75% methane, which can be used to displace natural gas fed to a boiler, be converted into green electricity, or be upgraded to renewable natural gas, eagerly sought by utility companies. Additionally, recycling hot water reduces the energy requirement to heat raw water to process temperatures inside the mill. With the passing of the Federal Inflation Reduction Act in 2022, there are significant tax credits available for biogas facilities for pulp and paper mills. Veolia hosted a webinar in December 2022 that specifically covered this topic. This webinar is now available on demand if you would like to learn more. The next few slides will show you opportunities for water and fiber recycle inside of a mill. There are two main strategies for water reuse or recovery inside a mill. Short water loop recycle. A typical example of this is whitewater treatment by dissolved air flotation, or DAF, where water that drains through the forming section of the paper machine is clarified and returned to the paper machine head box or stock prep area. This water is often called whitewater due to its color. This is water recycled inside the mill. This is the main area of fiber recovery too. Long water loop recycle. In this case, water is recycled from outside the mill back into the mill. This often involves end of pipe treatment at an effluent treatment plant where the effluent is cleaned and recycled back into the mill for reuse in various locations depending on the water quality of the effluent produced. The end of pipe treatment can be solid separation, biological treatment, or membrane filtration, but is frequently a combination of all these processes. This webinar will explore the two water recovery strategies in more detail. The goal of short loop water recycle is to recover clean hot water for use to transport mill or pulp inside the mill, whilst removing problematic compounds that are built up, like stickies. This process can also recover fiber that can be reprocessed inside the mill. Veolia's Poseidon and Saturn DAFs are some of the most common treatment processes for short loop water recycle, and often multiple Poseidon or Saturn DAF units are installed inside a single mill. Joseph will talk more about this in the coming slides. Long loop water recycle, as we mentioned previously, involves pumping recycled or clean effluent back into the mill. Veolia has various technologies for end of pipe treatment to remove contaminants like organics, salts, and solids. Veolia's bioethane anaerobic treatment systems are becoming more prevalent, often driven by environmental and economic advantages of biogas generation from starchy wastewater. Aerobic treatment systems, clarification and filtration systems like Veolia's ZWeed UF and ProFlex RO systems round out Veolia's comprehensive toolbox of technologies for wastewater treatment for recycled paper mills. This slide shows a simplified snapshot of the water cycle inside a typical recycled paper mill. Water plays a critical role in solubilizing the recycled paper into pulp and then cleaning and conveying the pulp to the paper machine. We will now look at short water loop recycling inside a mill, and I'll now hand it over to my colleague Joseph.
Thank you, Chris. So here we looking a little closer on a dissolved air flotation clarifier, or DAF clarifier, that's treating whitewater in a recycled paper or paperboard plant with a paper machine or paperboard machine, maybe a tissue machine. And these DAFs can be placed inside the recycle plant, or they can be placed on the paper machine whitewater, sending water back into the pulping plant, or sending water back to the paper machine for use in the showers. So we're going to talk a little bit about these applications. So Poseidon, since last year, has joined Veolia. We are a manufacturer of dissolved air flotation clarifiers, and we manufacture two types of units, as Chris had mentioned earlier. Both of them are space-saving designs. We have the rectangular ppm model shown here on the left side, and the vertical Saturn unit, which is even more space-saving, shown on the right side. And so when we talk about recycled paperboard facilities and recycle mills and inking plants, these plants are often in the municipal areas where they can get access to the recycled fiber. And real estate is often kind of at a limit. It's not like a big craft mill out in the forest where there's a lot of real estate. So we need to conserve space, and so we've come up with designs where small footprint type DAFs can be used in these recycle and dinking and paper machine whitewater loops. And we use them for, as Chris had mentioned, for water recovery as well as fiber recovery in some cases as well. So what are we treating? So I'm going to talk a little bit about short water loops. So in the dinking and recycling plants, quite typically we'll have 1 or 2 DAF clarifiers for water reclaim. So we need to get out a lot of the contaminants that build up in the water. We can have fines, stickies, waxes, sand and grit, fillers, inorganic material that needs to be removed. Otherwise, they'll keep building up within the loop. We want to reuse this water inside the dinking plant. If we're on a paper machine or paperboard machine whitewater loop, we want to clean up the water so we can reuse the water to some extent in showers and for dilution. At the same time, in addition to saving water and recovering water, we can sometimes recover the fiber depending on the quality of product that we're making. For example, many paperboards will try to recover as much fiber as possible, and where there are multiple layers, paperboard supplier manufacturers can take advantage of putting in the lower quality fibers, maybe some extent finer material into filler layers or bottom layers so they can hide away some of the recovered fiber that comes off the top of a DAF clarifier. And there we can see a photograph of some recovered fiber at the top of a DAF float. The DAF float on top of a DAF unit in a actually in this one is in a fine paper mill where they recovered some of the fiber. So some of the common fiber practices, we can recover some of the fiber from the paper machine. If it is of good quality, they can be reused, certainly in the recycle and dink plant. And quite often we'll see a scalping screen followed by a DAF clarifier. The scalping screen will save predominantly the longer fiber fraction, which can be of good quality for the product. The DAF will then do the proper clarification of the water so that the water can be reused. Sometimes that DAF float is not good enough quality because it tends to be finer. So sometimes the fiber at the top of the DAF may or may not be recoverable, depends on the product that's being made. So this is kind of a fractionation process where you have some kind of scalper screen to get the longer fiber followed by a DAF. And as I mentioned earlier, the recovered material can be sent to filler or bottom layers if the quality of that recovered material doesn't meet the specs for the quality of the top layer of the products. For example, if you have too many stickies or wax that may be present in the recovered material, then the reuse of that material may be limited. It may be bled in a little bit and may be rejected to some extent so that the paperboard plant does not build up too many stickies and wax in their system. Typically, we might see as one of our customers that I surveyed at a paperboard mill, they have a scalper screen followed by a DAF, and they recover fiber from both. And typically 3 to 5% of the weight of the finished sheet comes from these recycled materials. We can see a photograph at the top there of a reclaimed material DAF thickener on a DAF clarifier, and a type of a scalper screen here with the photograph furnished to us from Cadent for one of their Rotoflex type scalper screens. So Our product line, Poseidon product lines, as I mentioned, it's very important to have a small footprint in these recycled paperboard plants. Many times we're coming into the plant as a retrofit to replace an old clarifier that has seen better days. It might be 30 years old. It might, mechanically not in such great shape. So, or it's been undersized as production increases have happened over the years. So we sometimes have to come into a plant that's existing and try and shoehorn in a new piece of equipment while the old clarifier continues to run. And so you can see with the colored diagram there on the left side, conventional circular DAF clarifiers, which were like large flat pancake type units, tend to take up a lot of space, and that was the conventional type of technology in the recycled inking plants. And also rectangular units also tended to be quite long. So with Poseidon, we use plate pack technology inside of our units so that we can enhance the solid separation in the units with plate packs, or in the case of the vertical Saturn unit, conical shaped plates. And by doing this, we can reduce the actual footprint of the machine and the physical size, and you can see relative dimensions. So we end up with very high rate DAF clarifiers with smaller physical size that can fit into the recycled plants. So we're going to look at a case study here of a short water loop. So this is a paperboard mill in the Midwest US, paperboard manufacturer, and it needed to upgrade its recycle plant DAF clarification capacity because of an older inefficient unit that was under capacity. And so they needed to upgrade to a new DAF for water reuse and fiber reclaim. So some of the key drivers of the projects, of course, the increased sustainability by recycling the water and recovering the fiber, but also a small footprint was necessary because we had to shoehorn in an equipment into an existing space. So at this plant, the flow design is 1,300 gallons per minute to be treated. The inlet TSS averages about 1,500 ppm, peaks up to 2,000 ppm, and the DAF will provide clarified water at 100 ppm or less of total suspended solids, which can be recycled within the plant for reuse and dilution in the recycle plant. So the results, got a little ahead of myself, was the Saturn model due to its space restriction. This unit that was actually put in there was somewhere between 7.5 and 10 feet diameter. We have different size diameter units, so the floor space was very, very limited. And as long as there's enough height, sometimes the units can be put in through a second floor if there's a hole in the floor. So a space-saving vertical Saturn model was chosen due to the space restrictions, as well as the design of the unit being able to do the very efficient clarification of the water. So this paperboard mill has a two-stage system for reclaiming fiber and water. They have a slotted scalper screen with 20,000 slots in the screen, followed by the DAF. So the scalper screen will reclaim long fiber, which of course is, or longer fiber, which is valuable. And the fiber to the DAF tends to be 80% or so of the P200 fraction, so very fine material. And since the DAF floats up this fine material, and it's largely fines, it can improve the sheet density of the final product, but it cannot be used in all the grades. Sometimes they have to reject this material if it's not appropriate for the grade that they're making on that day. When you look at both the slotted screen and the DAF, you end up with about 3 to 5% of fiber by weight in the finished product. And the most important function of the DAF clarifier is in the reuse of the water, to keep water in the system and the energy in the system. And now I'll turn it over to Chris, that will talk about long water loop systems.
Thank you, Joseph. Joseph talked about short loop recycle. We'll now talk about long water recycle inside the mill, and how a mill can use their effluent to produce water consumption, energy, and use. This slide shows a simplified version of how wastewater can be cleaned at the end of the pipe and then returned back into the mill to replace fresh makeup water. Not all of the water can be recycled. For example, waste biosolids and RO brine are rejected from the system to prevent excessive buildup of TDS, or total dissolved solids, and other contaminants. What are the main challenges wastewater experts face with long water loop recycling in today's paper industry? Number one, the water is hot, over 100 degrees F, and getting hotter as water loops are closed. The hot effluent would need cooling for aerobic treatment. Two, high organic strength wastewater effluents result in high sewer fees when discharged to municipalities, and even notices of violations and limitations in discharges. Three, calcium carbonate used as a filler can concentrate up until it precipitates out when the pH increases. This causes problematic scaling in pipes and vessels. Veolia has developed a treatment process train that can solve all of these issues, allowing the hot organic wastewater to be converted into green biogas, even in a high scaling environment. We do this by producing a softened water stream that can then be used to reduce calcium concentrations to below precipitation levels, enabling anaerobic treatment. By implementing Veolia's treatment process, a mill can continue to operate profitably and sustainably by reducing operating costs and reducing their water and carbon footprint through recycling hot water. Mills are often space constrained, as Joseph said, and mills' operations have evolved over the years. The Veolia solution has a small footprint to fit into most sites. This technology train has been successfully deployed at several mills internationally and in the USA, validating our treatment process. Currently, as we mentioned, significant federal tax incentives are available to help improve ROI of these projects that generate and beneficially use biogas. This slide shows a typical schematic of Veolia's treatment process for recycled pulp and paper mills, with screening, flow equalization, anaerobic treatment to generate biogas, aerobic treatment and softening, and finally tertiary polishing for discharge or water reuse. This schematic includes anaerobic treatment. Over 700 of Veolia's biothane biobed anaerobic reactors have been installed worldwide since this technology was invented in the 1980s. Veolia continues to develop this technology to make the biobed high-rate system more robust and easier to operate and maintain. Biogas scrubbing and upgrading. We've discussed biogas extensively in this webinar, especially as it pertains to the investment tax credits or ITCs. Biogas must be beneficially used to be able to apply for these tax credits, not just flared. For example, used to displace natural gas fed to a boiler. Raw biogas contains hydrogen sulfide, or H2S, which is oxidized to sulfuric acid in a combustion device, for example, a microturbine, engine, or boiler. Veolia's sulfothane desulfurization technology scrubs the biogas to remove H2S to very low levels prior to beneficial use. In addition to the ITC, there are also additional tax credits available for the use of biogas as a fuel as RNG, or renewable natural gas. These credits include RINs and low carbon fuel standards in California, LCFS. To be able to benefit from these additional credits, the biogas must be upgraded to remove the carbon dioxide. Veolia's patented MEMGAS technology is a gas membrane separation device that separates the methane from carbon dioxide in a cost-effective manner to produce RNG. Softening. Veolia's patented technologies are used to remove hardness from the effluent to enable biological treatment and subsequent water reuse. Flotation, clarification, and filtration. Veolia has several technologies for solids removal, whether it be solids flotation after an MBBR system, clarification of a high concentrated mixed liquor activated substream, or final effluent polishing. Our technologies include Poseidon DAFs and Hydrotech disc filters. And finally, water reuse. Veolia is the world leader in filtration with products like ZWeed UF and ProFlex RO, both of which have been used to recycle effluent in long loop water recycle treatment trains. The purpose of this webinar is not to delve into each technology. However, if you would like to learn more about a specific technology, please feel free to contact us after this webinar. So the case studies on the next few slides will show how these technologies fit together for a long loop water recycle treatment process. The first case study is a recycled paper mill in Louisiana. This mill needed a new long loop water recycle system to meet increasing production capacity in a time critical manner. The goal was to be able to recycle some of the effluent back into the mill to replace makeup water. The wastewater effluent from the mill, generated by a previously installed Poseidon DAF, was hot, had high level organic pollutants, COD, and had a high scaling potential. All of the issues that we've discussed in this webinar. Veolia worked with the client to develop a technical solution using Veolia technologies to meet their needs. The solution that Veolia developed included wastewater equalization to balance out the flow and load. The next up was Veolia's patented bioethane biobed EGSB reactor that converted the hot, starchy wastewater into biogas, significantly reducing the organic load. The anaerobic effluent was then softened to reduce the scaling potential and fully treated using a custom designed activated sludge process. The biogas was scrubbed of H2S using Veolia's sulfothane technology and then fed to the site's boiler to reduce the natural gas usage. Parts of the aerobic effluent were sent to the sewer and parts were Veolia ZWeed UF and Proflex RO system to complete the long loop water recycle back into the mill. This slide shows some of the pictures of the Veolia system, the equalization tank and the anaerobic system in the top left, the biogas system in the top right, and then the two bottom pictures show the activated sludge system used to produce the final effluent. The second case study is a greenfield recycled paper mill in Kentucky. This mill wanted to upfront design a long loop water recycle system to minimize water usage. The goal again was to be able to recycle some of the effluent back into the mill to replace makeup water. This is a large facility that Veolia designed to be able to treat up to 1.4 million gallons a day of wastewater and up to 140,000 pounds of organic load, generating 28 million BTUs an hour of energy through biogas. The solution that Veolia developed was similar to the first case study. Wastewater equalization, Veolia's patented bioethane biobed EGSB reactor, softening, Veolia's sulfothane biogas scrubbing, activated sludge treatment, and then water recycle back into the mill. Part of the clarifier aerobic effluent is sent to the sewer and part back to the mill to complete the long loop water recycle. UF and RO polishing will be a future addition to enhance the quality of the water to be reused. In wrapping up this webinar, we wanted to discuss how a mill could start the process of considering short or long loop water recycle or fiber recovery inside their mill. When to consider a water or fiber recovery project. If your mill operations has been tasked with reducing the water use or is interested in fiber recovery, that could be the impetus to embark on a water or fiber recycle project. If you've closed the water loop, either through short or long water recycling or a recovering fiber, and you struggle to maintain quality control, that may mean you may need some form of water treatment inside your mill. If you have water issues from existing or new production that results in lower quality paper that chemistry cannot solve on its own. If you want to future-proof your operation to make it water resilient. If you're interested in biogas project to take advantage of tax credits. All of these are valid reasons to contact the Veolia team so that we can help you start on this journey or guide you through this process to a successful completion. We mentioned PFAS or forever chemicals previously in this webinar. PFAS has made headlines recently due to the state of Maine banning land applications of biosolids in April 2022. The EPA has been working to develop a PFAS strategy nationally. In October 2021, EPA's PFAS Strategic Roadmap 2021 to 2024 was finalized. It defined the overall PFAS strategy, including research, restriction, and remediation of PFAS. In December 2022, the EPA released their PFAS discharges in NIPD's permit memo. It is only for the EPA federally regulated NIPD's permit to gather data for future effluent limitation guidelines or ELGs on PFAS. It recommends quarterly PFAS monitoring in sewer effluents from selected industries including pulp, paper and paperboard industries. It recommends best management practices for PFAS elimination, reduction or source prevention. In January 2023, the EPA released their Effluent Guidelines Program Plan, which included recommendations to continue to monitor the anticipated reduction of PFAS use and discharge by pulp and paper mills through the Effluent Limitation Guidelines annual review process. The report states, importantly, because the production of PFAS-treated paper products is low and continues to decrease, and most recovered fiber is not generated from PFAS-treated paper products, it is unlikely that recovered fiber facilities would be a significant source of PFAS discharges. EPA is not prioritizing a rulemaking on the pulp, paper and paperboard point source categories at this time. In addition, the paper industry is planning to eliminate the use of PFAS by 2023, once again highlighting their commitment to sustainability. So thank you for joining this webinar and listening to Joseph and myself talk about the fascinating topic of water and fiber reuse in pulp and paper recycling facilities. I'll now pass it back to TJ.
Great, thanks Chris and Joseph for sharing your expertise and sharing some case studies about those various potential sustainability projects that recycled pulp and paper manufacturers could consider. We have a couple questions that came in throughout the broadcast. I just want to remind everyone, if you do have a question, there's time to ask it. On the right side of your screen, you should see that chat box, that question box. Go ahead and enter it in now, and like I said, we'll try to get to as many as possible before we close out the webinar. We do have one question that came in. It says, can the DAF provide stable water quality even if the solids loading or flow rate may vary? Joseph, is that something you could answer?
Yes. Well, first off, when we install a new DAF into a plant, it's sized for the maximum flow rate of water to be treated and the maximum suspended solids loading that will be in that water. So the DAF can run at lower flow rates and with lower total suspended solids. And so basically, if anything is, fluctuating in terms of flow rates or solids levels, if it's flow rates, we run the DAFs on a fixed level in the unit. So the water level inside the unit will always be at the same level. So if flow rates change, it's not going to change the treatment. If your solids loadings are changing, as long as they're not exceeding the design of the unit, then we're going to float them up just as well. So if the swings can be quite significant, then we can have an automatic adjustment to adjust the chemicals that we add. We're adding a flocculant, we may add a coagulant in some applications. So if the swings are quite large in flow rates and suspended solids, we can have automatic adjustment of the chemicals. If the swings are just minor, we may not have to do any adjustment. So the net result is we maintain a constant quality of water, clarified water.
Oh, great. I just a follow-up question, Joseph, about that. It has to do with the float or the sludge that comes from the clarifier, the DAF, the clarifier. How do you best dewater that? How have you seen that in the field to remove the water from that sludge? And is there another byproduct use? If it can't go back into, say, a filler sheet, can it be used or sold into another industry? Do you know of anyone doing that?
Yeah, so the float at the top of the DAF in paper processes will be, the consistency will be between 3 and 5% consistency. So if it's not of a good quality fiber to recover, then typically that will be sent out of the plant as a reject. It'll be thickened with a belt press or a screw press, typically maybe a centrifuge, but belt presses and screw presses are quite common to thicken that. And that could be contributed to some waste material that ends up being spread on fields, or it can go for if there's part of a bigger plant that might have boiler system and hog fuel. If this recycle plant is a part of a virgin fiber plant and there's some kind of fuel system, hogs fuel system, they could burn that. But typically it's taken out as waste and often can be used even as fertilizer. There's not really much there that can be used, sold as a product if it's not good enough to use in the pulp plant itself.
Great, thanks, Joseph. I got a lot of questions around this similar sort of subject. It has to do with calcium buildup. So Chris, questions, I'll just throw a couple out here and maybe you could tackle them all. With the calcium, can you talk a little bit about the process, about why in your wastewater process you have calcium sort of removal or softening after the biological step, the anaerobic step specifically? And can you talk about why it's ordered in that way? And then can you talk about, is it ever considered to maybe use some kind of physical chemical process or clarification to knock out those impurities before going to the anaerobic step?
So thank you, TJ. All great questions. The challenge relates to the chemistry of calcium carbonate in the water matrix. So often the wastewater that we receive, often in the effluent of a DAF system, for example, is saturated in calcium carbonate such that any slight adjustment in pH would result in precipitation of the calcium in our treatment system. So we try and maintain conditions and then precipitate the calcium out at the right spot so that we can manage that precipitant so that it does not scale or clog any of our process equipment in the anaerobic system. So that really is the key to our process design. So unfortunately, at the spot when we receive the raw effluent at the end of pipe treatment, it's difficult to precipitate it out without a major modification to the pH of the wastewater by raising it, and obviously the capital and operating costs associated with that. So we prefer to take care of that system downstream of the anaerobic system.
So truly, you're just managing the pH safely through to keep it from scaling within the anaerobic reactor, and then knocking it out right after it had time to reduce BOD and COD. Is that correct?
Correct, yeah. And each mill, unfortunately, is different. So these really are tailored solutions to each mill and their particular process and how much calcium they are using as a filler. So.
Okay. Another question, this goes back to the DAF. I know I'm flopping in between a couple of key technologies. Back to the DAF. Can you talk a little bit about the flow rates of the particular units? This particular attendee wanted to know the maximum flow rate for the vertical DAF, the Saturn DAF. Can you comment on that, Joseph?
Okay, somebody was asking about the different flow rates in the two type of DAFs.
Yeah, and then the maximum that, just say the Saturn DAF, the small footprint DAF could handle.
Yeah, okay, so we have a whole range of DAFs for both type of units, the rectangular and the vertical unit. And the rectangular unit, we have models ranging from as small as 50 gallons a minute right up to about 1,800 gallons a minute. And with these Saturn units, we'll start off with units that start off at about 400 gallons a minute, but that smallest unit could run at a smaller rate, at a lower rate. So somewhere between 400 gallons a minute up to about 1,700 gallons a minute on the Saturn as well. And so with the rectangular units, they basically get wider and longer, and in the vertical Saturns, we have different diameters as we go up in different size models. So we can have a 7.5 foot, 8 foot, 10 foot, 12.5, and 15.5 foot diameter unit. And those Saturns can range from anywhere from a little over 20 feet up to about 35 feet tall. So there's quite a range with many models in between, from 50 gallons up to 1,800 gallons a minute. And if you needed more than that, then you can have two DAFs installed.
Okay, thanks, Joseph. I'm going to go back to the biological wastewater treatment part of the presentation with Chris here. A couple questions. Can you talk about sort of the influent min-maxes for BOD and COD going into the reactor? Then what can you sort of expect of removal rates for BOD and COD? I guess, after the reactor, and what kind of removal rates maybe you could expect after the subsequent biological treatment steps?
Yeah, another great question. Thank you for that, TJ. So normally the concentration of COD or BOD on the influent depends upon the amount of closure of the water loop inside the mill. So we can see anywhere from 1,000 ppm of COD all the way up to 15,000 ppm of COD, all of which are amenable to anaerobic treatment, which is really designed based upon a mass load requirement of volumetric and organic loading rates. With the wastewater coming in hot, there isn't a requirement to heat the wastewater, so that removes one of the obstacles to anaerobic treatment. So hot wastewater is definitely good for anaerobic systems. In terms of the anaerobic removal, we normally get about 85 to 90% soluble COD removal with our granular anaerobic systems. And that obviously can get polished down to the levels that we need for discharge with the aerobic system, whether that be sort of 250 BOD TSS for a sewer discharge, or 1010 BOD and TSS if you're looking at water reuse back inside the mill, the long water loop recycle. And then obviously we leverage the ZWeed UF and the Proflex RO membranes to get the ultimate water quality that we need to sort of replace that raw water makeup. Does that answer the question?
Yeah, thanks for that, Chris.
Yeah, TJ, it's Joseph here. Can I just make a quick correction?
Yeah, go ahead, Joseph.
Yeah, I mentioned earlier that the largest units we had that go up to 1,800 gallons per minute. I meant to say 1,800 meter cubed per hour. That's 8,000 gallons per minute. So the range of sizes of DAFs is from 50 gallons a minute up to 8,000 gallons per minute.
Thanks for that quick conversion, Joseph. Appreciate it. A question here. We have an attendee that's running a TMP, a thermomechanical pulp and recycle mill. Can you talk about our experience with handling these kind of real high strength streams? They said that they have found that the stream can be toxic to anaerobic biological processes. Do you have anything to offer for that, Chris?
That's a great point. And when we encounter wastewaters that are a little bit unique, and part of that's driven by the chemistry of the water with the biocides that are added to control sliming on the paper machine. So we would strongly recommend a toxicity assessment of that wastewater, which we can perform in our lab in New Jersey, just to really evaluate whether the wastewater is biodegradable and any impact that could have on the wastewater. And once again, that's often chemistry that's introduced into the stream to be able to control the wet end chemistry of the paper machine. So that is certainly something that we could discuss with the client to see if there's a way to modify the chemistry, or see if there's a different stream, or just see whether it is biodegradable or not, or toxic to anaerobic treatment.
Great, thanks for that. Just looking through the questions here. I think I got to most of them. Oh, here's one. In a closed loop recycling mill, what's the best strategy to avoid ash buildup? What parameters would you look at to see if you have cycled up your system too much without purging the loop? Does anyone want to answer that question?
Yeah, what was the first part of the question?
It says, in a closed loop recycled mill, what's the best strategy to avoid ash buildup?
Well, probably the best strategy is to use the DAF clarifier. And typically, because we're going to float up the ash that's in that water, and then you're going to recycle the clarified water. So typically the DAFs are going to be used in tissue recycle plants because the tissue paper machines need to limit how much ash is in their pulp going to the tissue machine. So the DAF clarifier is an excellent way to get that float out. So basically what you're going to float, you're going to reject, and you'll reuse the water.
Thanks, Joseph. Another question here that came in has to do with sulfur within the water streams. Have you had any experience or thoughts in be able to precipitate out and then and capture that sulfur within a water circuit?
Should I take that question?
Please.
Yeah, so any sulfates that are in the wastewater will be reduced to basically sulfides in the anaerobic treatment system. And with those treatment systems, we often need to add iron as a vitamin or macronutrient to the system. And obviously the presence with iron with the reduced sulfur is going to create iron sulfide, which will precipitate out in the reactor. There is going to be some of the sulfur that's converted into hydrogen sulfide that will be in the biogas. And as we scrub the biogas scrubber actually generates elemental sulfur from the hydrogen sulfide. So we do generate a solid sulfur stream from that system. However, to date, we've struggled to find economically viable outlets for that sulfur. So if anybody has any ideas about that, please feel free to contact us. We're more than happy to talk about that.
Okay, we have a little bit more time, just some more questions popped in here. It's basically, how does the UASB reactor provide, how's the BOD and COD removal when compared to an AHR? I don't know if you have any comments on that, Chris. Maybe another question with that is the AHR prone to face clogging issues of the media? Can you comment, or do you know of any customer experience with that?
So I'm not particularly familiar with an AHR reactor, but I presume it's a combination of a granular and a fixed film reactor or fixed bed reactor. So obviously, anytime you have a fixed film or fixed bed, that's going to be prone to seeding crystallization of any precipitate that's going to be present, in this case, calcium carbonate. So it would be very important with a system to control the precipitation into an environment and a stage in the process where you want it to precipitate out, where you can manage that solid component. What we've seen is that the EGSB tends to be a little bit more amenable to this process than a UASB, just because of the more vigorous fluidization of the bed. So there's less risk of precipitant accumulating in the bottom of the reactor. And we certainly design for precipitation so that we can remove it from the bottom of the reactor as necessary. So to date, the technology has been more EGSB, which is an expanded granular bed reactor, rather than a UASB outflow anaerobic sulfur bed reactor. So of the three technologies, AHR, UASB and EGSB, we would certainly recommend the high rate granular EGSB, just because of the more vigorous mixing and the less potential for scaling and crystallization inside the reactor, posing problems with the reactor in terms of structure and effective use of the volume being taken up by inorganic materials. So sorry about the long-winded answer.
No, that's fine, Chris. Thanks for taking that. I think I got to most of the questions. If there are additional questions that pop up after today's live broadcast, my information's been on the screen there. You can email me and I'll get it to the best technical resource for you to help you out there. My phone number's there as well. At this time, I just want to remind everyone to take that short survey after the webinar. It'll be really helpful for us in planning these events in the future. That'll be great, and we'll enter you in that drawing for the Amazon gift card. So at this time, I'd like to thank both our presenters, Chris and Joseph, for preparing this presentation and sharing all the case studies and all of the strategies and experiences that they've encountered over their multiple decades of working with pulp and paper facilities. And I'd like to thank, most of all, everyone here who spent an hour of their day or so just learning a little bit more of the trends related around the water reuse and fiber recovery. So we'd like to welcome you back on a future webinar. Check our website frequently to see any new events that are happening. And just want to wish everyone a wonderful day. Thank you. Take care.